Okay, let's get started. So I'm Max McMullen. I'm the development lead for Direct3D at Microsoft. My team designs the Direct3D API for all Microsoft platforms. Today I'm here to give you a preview of the Direct3D 12 API. So just some upfront goals and assumptions for the whole talk. As I mentioned, this is a preview of D3D 12. We're intentionally engaging early with developers across the 3D API ecosystem. The idea is we can get feedback and refine the API over the course of our shipment cycle and avoid any unexpected perf hitches or problems with the API design when we finally ship. So as we progress throughout our ship cycle, we'll have more API talks. I'll be talking about more and more details in future talks. Please just watch out on the DirectX blog or on the DirectX 12 Twitter hash to watch for when those talks occur and you can get more details. So the idea today is just to give you sort of a, broad strokes, painting the picture, what we're doing moving from D3D11 to D3D12. So I am going to assume just a baseline of understanding D3D11, roughly how it works. And I'm going to walk you through step by step how we got from 11 to the now console level efficiency of 12. So that's the talk. That's roughly what our goals are. What is D3D12? As I mentioned, D3D12, our main goal in just a single sentence is console level efficiency on phone, tablet, PC. Then on Xbox One, our goal is even greater level efficiency and parallelism than the existing API set on that platform. What do I mean when I say console level efficiency? Two main areas. CPU efficiency, so how much CPU work is necessary for generating a sequence of state change draw pairs. And then CPU parallelism, so how efficiently can you scale out across as many CPU cores as you have, generate rendering commands or other rendering work across all those cores, and then submit that work to the GPU. Fundamentally, the way we're going about this, we're giving you, the developer, more control of not over parallelism, but how you manage GPU memory, GPU resources, and how those resources can be leveraged to issue rendering commands. At the same time, we didn't want to take anything away from you. So all the existing rendering capability that D311 provides is available on 12. And in fact, we're going to continue the process of adding new rendering functionality as GPU hardware becomes available with new features. Okay. So as I mentioned, I want to walk from D311 and build up step over step what D3D12 is. The talk I've really split into two halves. First half, CPU efficiency. How can we make it more efficient to generate rendering commands with a CPU? How can I make it possible to reuse rendering commands so your app isn't generating the same sequence of commands frame over frame? Second half of the talk, I'm going to talk about CPU parallelism. So not only can you efficiently generate commands, but how can you efficiently do command generation across multiple threads? That's the second half. So starting with D3D11, what you see on screen is just a graphical representation of what the D3D11 rendering context is. So from left to right, on the left you see a bunch of arrows. Those arrows represent individual pieces of pipeline state on the D3D11 rendering context. Each one of those can individually be set or retrieved from the API. But as a collection, that pipeline state represents what the GPU will execute when a draw or dispatch command occurs at the API surface. Next to the arrows, those are the individual pipeline states. These are the same ones in 12 as 11. Things are broken down from an input assembler to a vertex shader to geometry shaders. In 11, there's tessellation, so domain shaders, hull shaders. Finally, pixel shader and output merger that you've probably seen before in 3D APIs. At the bottom, there's this collection of other state, and it'll be obvious later why I've separated that out. That's mostly just some simple fixed function state, things like viewports, scissorx, that we want to keep separate from the overall graphics pipeline. I'll explain why again later. Next to each stage in the pipeline, you see those arrays of red rectangles, and those represent the bind points in D3D11. D3D11, like a lot of APIs, 3D APIs before, both in the D3 space and in other graphics API families, has an explicit bind model. So every stage in the pipeline knows exactly what resources it could refer to. Each of those bind points, in turn, refers to resources in GPU memory, everything from buffers to UAVs constant buffers, textures, render targets, volumes. So we have a fine-grained set of pipeline objects. Each individually can be set and retrieved. We have explicit bind points that are part of the rendering context that each stage can refer to. And then finally, those bind points can refer to a variety of different types of resource. Let's talk about CPU overhead and how we can make it more efficient to generate commands than were possible on the 11 pipeline as it is today. So the first piece of command generation we want to optimize is how to make that state change draw pattern more efficient. Let's optimize the state change portion. This has been a recurring pattern in 3D API design, and 12 we take it even further and get much greater efficiency out of it. So when we went to D3D10 from D3D9, we took even more fine-grained states and grouped them together into these shader stages. So what you see now is the rasterizer state actually in D3D9 was a collection of even more fine-grained states. Each individually could be set or retrieved. So 10 combined them all into these objects, and that did provide some measure of CPU efficiency. It got us some integer multiples of performance in terms of managing state. But what it left on the table was there's still some overhead in the drivers taking that collection of objects and resolving them all into one coherent set of GPU code that executes at draw or dispatch time. Let's just call this the hardware mismatch overhead. The way most drivers on D3D resolve this mismatch, where setting an individual pipeline state might not be a single piece of hardware state, is they actually record all the set commands and then defer resolving them until draw time. It'll be obvious in a second why that actually causes some overhead. So let's, again, just take a visual approach. I'm a visual person, being a graphics guy. So on the left, what we have here, if it wants to advance, there we go. This is basically a D3D9 style pipeline. It's probably the most common style pipeline used by applications today in 3D. Just a vertex shader, a rasterizer, a pixel shader, and a blend state. None of the more advanced tessellation or geometry shader routines. So that's the pipeline. That's what the application, an application is using to represent its draw call and parallelize across all the pixels. On the right-hand side, this is actually what the hardware needs to be programmed. And while this is sort of a made-up case, it actually does end up true for most hardware that the top, we can say hardware state 1, that sort of represents shader code. Those are actual GPU instructions executed on the shader cores. Hardware state 2, you can imagine, is the combination of the rasterizer state and whatever control flow is necessary for linking the vertex shader to the rasterizer to the pixel shader. Hardware state 3 is effectively the linkage between the pixel shader and the blend state. And so you can imagine that's just how you take the pixel shader output, fork it out to all the different blend functions, and finally write out to the render target. So if a driver wants to actually emit GPU commands for the application setting a vertex shader, it would have to program both hardware state 1 and hardware state number 2. If then the application goes and changes the rasterizer state, the driver would also have to emit hardware state number 2 again. Next, the application changes the pixel shader state. Well, the pixel shader actually affects all three because it has shader code, it affects the linkage from the vertex shader to the pixel shader, and it affects the linkage from the pixel shader to the blend state as well. Finally, the blend state actually affects both the shader code and the linkage between pixel shader and blend state. So a bunch of mobile GPU architectures, the blend is actually implemented as shader instructions. So some GPUs have fixed function hardware, some have shader instructions representing blend functions. The end result with this complex overlapping state is most drivers don't want to emit the GPU commands at the same time that the application sets a vertex shader or a rasterizer. All the drivers defer, they record those state sets, and they defer and wait till draw time so they know actually what the application is going to use. And then finally, they spend all the CPU effort to record, mark things as dirty, and finally at draw time they have control flow to detect, oh, my state's dirty, I actually better program the hardware to match the API pipeline state that the app set, and it emits those hardware states at the end. What would be ideal actually is the application sets the pipeline state, and the driver knows this is what the application intended. I'm going to go program all the hardware state once. No control flow, no extra logic recording commands, and then resolving them at draw time. Just a simple set and then corresponding hardware state set. So in the D3D team, what we did is we recorded a bunch of applications and just looked at the end-to-end pipeline from the input assembler all the way out to the output merger. We said, well, what if we grouped all these together into one entire pipeline state object? How many of those are there? Is that a tractable number to bundle all together? What we found is that there's about, for a typical modern game or desktop workstation application, at most we see about 200 to 400 complete pipeline states per frame. If we look at a longer recording over the course of, say, a minute, there are a total of about 500 to 1,000 unique sets of pipeline state used by an app. And that may sound like a lot, but actually that is a very tractable number. An application could effectively build all those pipeline states and just swap between them if it wanted to. And in fact, we know this is true because a lot of drivers cache the pipeline states and do hash lookups to pull the combined pipeline state out of their internal driver cache. So the 12 model is we group them all together. And instead of doing this deferred tracking and finally resolving the state at draw time, 12 just, when you set a pipeline state object, the driver knows exactly what hardware state to emit. Now, if you remember back the pipeline diagram, I separated some things out at the bottom, and I called it other state at the time. One of the goals for this pipeline state grouping, we didn't want to have the number of pipeline states explode. And it was important that an application is able to change the render target size without affecting a compiled pipeline state object. So things like the viewport and the scissor rex are actually left orthogonal to the overall PSO object. And that doesn't turn out to be a performance problem because most hardware can program those orthogonally to the rest of the GPU pipeline. So what you see on screen is the 11 rendering contexts I mentioned earlier. And now this is what it looks like, changing from a fine-grained pipeline state object model to a coarse-grained object representing all the shader code with a single set and get. So that's pipeline state change overhead and how we optimize in 12. Let's move on and talk about resource binding overhead. So resource binding, at the API surface, it seems like a relatively simple concept, and one of the common points of feedback I've heard from developers using D3D, I'm setting a pointer. Why isn't it as efficient as setting a pointer? And the fact is that resource binding has been part of 3D APIs for a long time. It even precedes D3D. And a lot of pieces of the system have been built up assuming a resource binding model. The D3D runtime and the driver, and in fact other API families in the driver, use resource binding to manage multiple properties behind the scenes, all in the name of helping your app efficiently emit rendering commands. So first thing that's used, the bind points are used for resolving resource hazards. And as an example of a resource hazard, switching from a resource being a render target to being a texture. I'll explain more in a second what a hazard is and how we optimize it, but when I talk about hazards, it's usually transitions like that. Resource lifetime. So D311 and other pre-D312 APIs typically try to abstract the idea that all the commands to the GPU are queued. The API tries to behave like when you call draw, the GPU immediately goes and issues a draw. What's actually happening behind the scenes is there's a queue of commands. Everything is deferred and then executed at a later time by the GPU. This deep pipeline enables greater efficiency parallelizing between the CPU and the GPU. But what happens is there's a lot of reference counting and resource lifetime tracking going on behind the scenes that takes CPU effort. And ideally, you could get deep parallelism across CPU and GPU, but not pay that CPU cost for tracking resource lifetime. Again, I'll talk about that in a bit, how we solve that. Finally, resource residency management. Similar to the resource lifetime, behind the scenes there's a video memory manager, and applications typically want to use a lot of GPU memory. In fact, more memory than there's actually available on, say, discrete cards with a fixed budget of 1 gigabyte of resources. So the bind points enable the operating system, the driver, to page things in and out of video memory as the commands flow to the GPU, thus making it look to your application like there's an infinite supply of video memory available, but at the cost of, again, reference counting and lifetime tracking and tracking which resources are used at which point in the command stream. Last, there's a secondary issue. This isn't the primary primary place where CPU overhead is spent, but it does actually show up once we optimize the first three. And that is the runtime mirrors all the state. So when you set a resource binding, the runtime tracks that, puts a ref count on the object, also that your application can call get later and find out what it bound to the pipeline originally. This was an ease of use for middleware, so you can have componentized software find out where the rendering context currently is. And so once we optimize the first three, the overhead of ref counting and tracking what was set becomes apparent in the API and in the overall graphics pipeline used by applications. So let's walk through those three main issues: resource hazards, lifetime, and residency management, and see how 12 has changed things to get greater CPU efficiency. Hazard resolution. So I mentioned the basic idea. If you have a render target, your app is, say, rendering a scene, and that scene is actually meant to be an environment map around your final rendered scene. So your application would issue rendering to that render target, and then at some point, rendering the scene graph, your application decides, okay, I'm done rendering this environment map. I want to use it as a texture now. Well, the runtime and the driver are tracking when something's bound as a texture and when something gets bound as a render target. And if they ever see something bound as both simultaneously, the runtime and driver forcibly unbind the oldest setting and respect the most recent setting. That way, when your app is issuing rendering code, you can switch from something being a render target to being a texture, and the graphics stack manages all the bindings behind the scenes. The other thing the driver is doing is when it detects this hazard, there's actually a deep pipeline of pixels in flight in the GPU at any point in time. And if you're going to start reading from a texture before those pixels have retired in the GPU, then you wouldn't actually have coherent state. So it's necessary for the driver to flush the GPU pipeline before a render target could be used as a texture. If I were to take a step back and describe hazards in a general term, what a hazard is whenever there's extra work that needs to be done in the GPU to ensure your data is coherent. There are a couple other examples. I've been focusing on the render target texture transition. There are cases where memory is getting reused for the tiled resource feature that we just exposed in Windows 8.1 on D3.11.2. There are other cases where, say, compute is being used. So back-to-back dispatch calls using resources, you want to have a barrier to ensure that one compute task is complete and written to memory before the next compute task starts. So implicit resource tracking, the runtime is looking at bindings, it's looking at render target output. How do we make that more efficient? Well, in a pattern you'll see multiple times throughout this talk, we're making it explicitly app controlled. So why should the runtime be doing all this fine-grained work when you call bind on a shaded resource view or bind on a render target? Why are we doing this tracking when in your application, it's really just one point in an entire frame. In a 60th of a second, you'll switch from using something as a render target to a texture. By making it application explicit control, we can get rid of all that fine-grained cost and pay the overhead once when your application actually wants to make a resource transition. What you see on screen is the actual resource barrier API we added to 12. So it's fairly straightforward. It declares a resource. It declares a source usage for the resource and a target usage for the resource. And then finally, there's a call to tell the runtime and the driver about the transition. That's actually an arrayed call. So if your application was, say, transitioning multiple resources, like a render target and a depth stencil, from those resource types to textures, they can both be declared in a single API call, and the driver can emit the optimal sequence of commands to make sure your data is coherent for both resources at once. So we went from something that involves walking and tracking across arrays, conditional logic, figuring out what type of transition to emit, to something that's very explicit, something your application already knows, and it reduces all that, pulls all that logic out from a high-frequency bind and draw time and makes it just single time per frame or whatever frequency your application makes transitions. That's hazards. Lifetime and residency are similar. I'm not going to go into too many details about the API surface here, but it's the same solution. We're actually giving your application explicit control. 12 no longer tries to hide the queued nature of the GPU. So your application is similar to async file I/O. Your application knows that it's emitted a sequence of commands to the GPU, and those executed at a future point in time. In 12, we added an API, a fine-grained fence API. So on the CPU side, your application can find out how far the GPU has progressed. And once the GPU gets to a safe point in the rendering stream, your application can then delete a resource or create a resource. So instead of the runtime watching a bind point, ref counting, tracking that ref count through all these commands, then releasing the ref when the GPU's executed them, your application can look at a coarse grain basis, say once per frame, and say, okay, all these resources that are referred to in this frame can now be deleted, or this memory can be reused for a different resource type. That's resource lifetime. Residency, again, explicit application control. Instead of D311, where we're tracking ref counts and tracking the control flow in the OS, your application typically already would know, this sequence of rendering commands is referring to this set of resources. Explicitly move them into video memory, tell the OS, move them in, I'm about to use them. Then later on when the commands are complete, your application can explicitly tell the OS, move them out, I'm done. So with those three changes, we've gotten rid of implicit tracking of hazards, we've gotten rid of ref counting for all the resource types in the bind slots, and all the conditional flow control necessary to make that work behind the scenes at a fine-grained basis. Instead, the overhead happens in your application at only the granularity necessary for your particular rendering algorithm. Last, once we get rid of all that resource counting, reference counting, lifetime management from the runtime in the OS, the actual state mirroring cost starts to show up in our profiles, and we've just removed the gets. Typically, what we found is most applications already know what the current state is and can communicate explicitly to middleware about what they want the middleware to do, or whatever they want the componentized software to do with the rendering pipeline. So, to be clear, all the CPU overhead, the vast majority was in removing the ref counting. When I show you this rendering pipeline, it's going to look really simple. We've just gotten rid of the gets on the arrows. But in fact, we've removed a lot of CPU overhead doing really fine-grained reference counting and lifetime management behind the scenes, and removing the gets is a secondary issue. But nonetheless, that's what the pipeline looks like at this point. So I've told you how we've just optimized the efficiency of generating commands, both from the state set point of view and reducing the overhead and resource binding. But it would be great, actually, if your application didn't have to redo the work from one frame to the next if the exact same bindings were being emitted. And that's exactly where we're going to look next. So typical applications, again, we did some analysis on rendering patterns. And typical applications actually generate the exact same sequence of commands from one frame to the next. I'll give you some numbers later, but it's quite coherent. And it's not only true of the rendering command, but it's also true of the bindings. So if your application in one frame is going to bind 16 resources to draw an object, then the next frame, it's going to use the CPU to regenerate that same set of 16 bindings and send them to the GPU. Why not be able to cache that set of bindings and just emit a simple command, oh, I want to reuse that set of bindings from the previous frame. It'd be much more efficient. A second detail here, not only is there overhead in re-emitting the exact same thing from one frame to the next, but the actual implementation and drivers, they have some internal data structures tracking all the bindings. And to make the GPU look like commands happen immediately instead of happening in a deferred queued basis, they actually, if you change, say, the first of 16 resources, the driver's going to copy all 16 bindings, all those data structures to a new location, edit the copy, and then tell the GPU to start using the bindings from the new location. So whenever you make a partial change to bindings, so like some set of resources are static and some are dynamic, the entire set has to be copied and reset. Ideally, if we had a design that would enable your application to do different frequencies of update and not pay the CPU cost for copying those bindings. So what we have in 12 is a solution we call descriptor heaps and tables. This is, you might have heard of something called bindless rendering. This is sort of a take on bindless rendering, but this API design actually scales across the extremes of hardware that D312 supports. Everything from the smallest SoCs on phone doing feature level 9.3 all the way up to the largest desktop GPUs that are fully 11.2 capable and beyond. This unified approach using explicit heaps and tables allows a wide variety of rendering techniques, everything from 11 style streaming updates from the CPU every single draw to the ideal world where you can cache all the bindings up front and then just reuse them from one object to the next. In the case of in-between rendering modes, this new descriptor heap and table model actually allows having 2 different frequencies of update, or in fact even 4 frequencies of update, where you can cache certain sets of resource bindings and reuse those, meanwhile have a small table of things that are dynamically changing from one draw to the next. And that's without having to recopy the entire set of bindings from one draw to the next as the high frequency items change. Last, the model also enables a new feature where in your shader you can dynamically index across all the bindings. So you could stream in a constant or stream in some vertex parameters to pick the texture instead of having to fix function code and program the binding up front when the draw is issued. So that's what descriptor heaps and tables provide. Let me actually describe what they are. And let's look at just the atom of this whole model. What is a descriptor? Really, a descriptor is just a struct on the GPU, in the GPU memory. And that struct is actually what used to be behind the D3D11 view object. It's really a dumb struct. There isn't any hidden memory allocation that's behind it. It's just an opaque chunk of memory. That chunk of memory has a type for the resource, some parameters. In the case of a texture, it'd have things like the MIP count. And finally, it has a pointer to the actual pixel data for that resource. So in 11, when you set a binding on a shader stage, the driver behind the scenes would actually take the view object, copy the descriptor to the current location in the rendering stream where the GPU is reading descriptors, and then have the GPU read from that while it's sampling. If you then set another view in the same spot, they would copy all the descriptors to a new location, pipeline a command to say, okay, once that draw is complete, start using this new copy of descriptors and stream from this location instead. That's what 11 did. And now we're going to give your application explicit control over when these descriptors are created, when they're copied, and when they can be reused. And that's what descriptor heaps are all about. Descriptor heaps effectively are just a giant array of descriptors. And how an application, say in the past, would use vertex buffers and index buffers and rename them, you can have a descriptor heap and then fill in a set of descriptors, either stream in more sets over time from one draw to the next, or you can actually go back and reuse descriptors that your app already streamed into the buffer. So your app is in complete control over the layout of this. It's just a giant array filled with these descriptor objects. It's low overhead to manipulate. Effectively, it's data copies. The actual contents are opaque because they vary from one GPU architecture to the next. But in general, it's just array manipulation and copying, or pointing back to the same location in the case of reuse. Depending on the generation of GPU, older GPUs or lower power GPUs have limited descriptor heap sizes. At smallest, they can have 65K descriptors in a single heap. On the high-end GPUs, they can go up to being memory limited, so effectively, 2 to the 32 total descriptors. In the case of those small GPUs with 65K, in a single frame, your application's rendering might actually exceed that quantity of descriptors. So the API allows allocating multiple descriptor heaps and then switching from one descriptor heap to the next. It'll be up to your application code, to try and minimize the number of descriptor heap changes, because that in some GPU architectures is a GPU pipeline flush. But overall, you have the power to do reuse and to stream at whatever frequency is necessary without having redundant costs from one frame to the next, reissuing the same descriptor bindings. So I've talked about descriptors. I've talked about descriptor heaps. The next question is, well, how do I associate my shader code with a particular chunk of descriptors in a given draw call? Like, how is that parameterized? And that's where the descriptor tables come into play. A table actually isn't an API object. It's literally just a notion of a start index and a size. And you have one or more of those start index and sizes per shader stage. So in a pixel shader, you could point to a particular location in the descriptor heap and say, this pixel shader cares about the descriptors from offset 4 to offset 16 in the heap. And then when the next call is issued, a command can be streamed to the GPU saying, this next draw call, instead of 4 to 16, it should be 16 through 28. So it's not an API object. It's just a lightweight piece of state that's stored in the GPU shader cores themselves, indicating which descriptors to use for a given draw call. Now, I've mentioned multiple times the idea of independent frequencies of update. Well, actually, early GPUs only get a single table per shader stage. But as GPU hardware evolves, we actually have the ability to expose multiple tables per shader stage. So a pixel shader can have 2 tables, or 3 tables, or 4 tables on modern hardware. And you can have one table be the high-frequency things that are changed draw over draw, and then a different table refers to the things that are static and actually might be static across your entire rendering scene. That way, we can avoid copying the entire set of descriptors from one draw to the next, and instead only copy the things that are being changed dynamically. So back to our modified 11 pipeline. This diagram shows removing the gets, and it shows the pipeline state object change. Now let's take the resource binding model and shift it over to what it looks like with descriptor heaps and tables. So the context no longer has explicit bind points. Instead, there's just, as I mentioned, a table or more per shader stage, and then overall the context has a pointer to which descriptor heap is currently active. You can see in the pixel shader I've shown in the diagram that pixel shader has 2 tables. One table could be the high frequency textures that are changing from one draw to the next. The other table can be pointed to a resource that's like the common lighting environment for a lot of draws in a row. The descriptor heap there, each descriptor points to individual resource types, and your application can reuse those descriptor entries from one frame to the next, reuse them from one draw call to the next if necessary, or in the case of things that are dynamic, just build either a linear allocator or a heap allocator, however you choose. It's just memory your application can manage on its own. And this is actually what the D3D12 rendering context is. So we've moved from fine-grained state objects to a single pipeline state object, and we removed all the hazard tracking and the mirroring of state with the get calls. Finally, we've moved from the very heavyweight context with explicit bind points to one that's memory objects and application managed with the descriptor heaps and tables. So we're almost done with the CPU efficiency side. We'll get to parallelism in a second, but there's one last detail to go over. I mentioned applications issue the same commands from one frame to the next. And so not only is it about the bind points, but it's about the commands themselves. So we used the longest common subsequence algorithm, modified it to track GPU commands. And what we found is typical applications have 90 to 95% coherent set of rendering commands from one frame to the next. So if you looked at the sequence of state set, resource bind draw, state set, resource bind dispatch across an entire frame, only about 5 to 10% of those commands are deleted or added from one frame to the next. And it'd be great if your CPU didn't have to keep doing the same thing over and over again. So what we wanted to do is we wanted to give your applications a way to reuse that sequence of rendering commands. It's again, this has been debated back and forth in API design for a long time. Things like OpenGL display lists are an example of command reuse. The problem was, and the reason why D3D has never embraced this yet, is it's very hard to build a way to record commands that is both conformant and reliable, so it behaves the same way across multiple different GPUs on multiple different drivers. And simultaneously with that, make it performant, so your application can count on those recorded commands being played back much faster than it would be had your application called the individual commands to begin with. So the thing is, the changes we made to the pipeline state object and the changes we made to move to descriptor heaps and tables dramatically simplifies the type of state necessary to record and play back commands. And at this point, with the 12 design, we believe we can build both a conformant, reliable, and efficient recording of rendering commands in D3D12. Oops. So we call them bundles, command bundles. Effectively, it's a small list of commands that your application can record. They're recorded once, and then they can be reused multiple times. They can be reused multiple times across frames. They can be used multiple times in a given frame. The reuse is unlimited. They can be created on any thread you want. So you could spawn a worker task when an object is first encountered on the scene and say, this object is encountered, I want to record a bundle for all the rendering commands. And that can be recorded once and played back later. So command recording is great, but ideally it's parameterized in some way. Things want to change on screen. And the bundle model allows parameterization of the bundles. And that's where the descriptor heaps and tables come into play. So a bundle of commands can inherit the input table bindings from the parent command list, the parent context issuing rendering commands. So your application could say, set the constant buffer bindings, then execute a bundle. Set a different set of constant buffer bindings and execute the bundle again. Those two bundle executions would be parameterized by those constant buffers and look different on screen. So we get command reuse, but we get parameterized command reuse with efficient generation of commands on the CPU for the GPU execution. Last, we had to put some restrictions in the bundle, like what can be recorded. And that just makes sure that the drivers can record efficiently and play back efficiently. The basic detail is no rendering commands that change the render target. This was a concession to tile-based renderers where some immediate renderers don't have a problem changing render target frequently, but a tile-based renderer wants to capture a whole scene without having to flush all the tiles to GPU memory. So bundles do not have the ability to change render target. They can't do things like copy, where copies are effectively implemented with a render target change under the covers. But in general, that still leaves a large amount of rendering that can be recorded into a bundle and optimized. So let's just go through a brief demo showing the control flow happening in the GPU command processor with a bundle. So what you see on the left, that's just representation of a rendering context. There are a sequence of commands there. Those have been generated by the CPU and turned into GPU commands. And the GPU command processor is going to be walking through all those commands. On the right, you see two bundles. Those bundles have already been recorded on different threads, and the command processor is going to, at appropriate times in the control flow, execute the commands in those bundles. So command processor starts executing. Maybe. There we go. So what you saw is just the GPU went, executed the clear, draw, set table, and then it gets the execute bundle. Now the command processor follows the control flow, executes all the commands in the bundle, and then pops back and starts executing the main context again. So it sets table, then it gets to the next execute bundle. The command processor executes that bundle, goes back to the main context, and executes whatever rendering commands remain. So that's how bundles can be pre-recorded and used to issue the same rendering commands on the GPU multiple times. So that doesn't show you the CPU efficiency. That just shows you the control flow on the GPU. This is a representation of the actual CPU commands and API calls necessary for issuing some rendering. There's a setup stage at the top. The font's small, the details don't matter too much. You see a setup at front, then there are two objects being drawn. The rendering commands are identical for those two objects. The first object has one set of constants, the next object has a second set of constants. But otherwise, the pattern of setting shader resource views, drawing, setting shader resource views, drawing is the same between draw 1 and draw 2. So let's record those two objects and just be able to play back the bundle, parameterizing that bundle with constants. So top call is creating a bundle. That can happen on any thread in your application. It can happen on a task spawned by your whatever parallelism thread manager you have. Then on the bundle object itself, a sequence of commands are called. In this case, it's setting the topology, setting the shader resource view table, draw, set shader resource view, draw. And finally, that bundle is closed. At close time, the driver bakes all those commands into a set of GPU commands. So this is what it looks like using bundles instead of no bundles versus bundles. On the left, the same code as before. It's a setup, drawing two objects explicitly. On the right, simplified setup, because some of it's recorded in the bundle. Then the constant buffers are set, bundle is executed. A different set of constant buffers are set, and the bundle is executed. So the total number of CPU calls to the API is dramatically reduced, but the GPU is executing the same sequence of commands. And that's how we get our CPU efficiency. Let's just show a brief demo. Okay, so what we have here, this is a sample. It's a ported version from an 11 sample. So you might recognize this. This is the cityscape from the instancing sample. It's actually, let's see, a rather large number of the cities. And in the top line, you can see just performance in terms of FPS, and then the amount of CPU time in milliseconds spent to render that frame. So without bundles, it's taking approximately 0.75 milliseconds per frame for the CPU to generate all the rendering commands for the GPU. This is without bundles. Now let's run the same version with bundles. And instead of 0.75, we can see it's actually less than 0.1 milliseconds. And I can change the scene so you can see we're running roughly the same FPS for the same scene, but with an eighth the CPU overhead. Admittedly, this is just a sample. It has a relatively simple rendering loop and simple content compared to a real application. At the end, I'll show you another demo of a real engine using bundles and the CPU overhead savings on that real engine. Okay, that's CPU efficiency. So we've covered how to reduce the CPU effort in generating a sequence of rendering commands. I've shown how to reuse rendering commands and reuse bindings to get even more CPU efficiency. Now let's talk about parallelism. So when I've been talking about the context, the rendering context, I've kind of been implying that it's immediate. When you issue commands, the GPU will execute them and thereafter. But what we've done in 12 is actually, there's no more immediate context. Everything is a deferred context. It's all, you can have threads generating commands in parallel, completing that list of commands, and then submitting it to an explicit API object called the command queue. So the GPU won't execute commands until they're submitted on that queue. The queue represents the ordering of commands. The command list represents the recording of those commands. The difference between a command list and a bundle, command lists are optimized for one-time generation of commands. So you can have multiple threads efficiently generating a sequence of rendering commands on multiple threads at once. You use that command list once, and then you can delete the memory and record a new set of commands in the next frame. The command queue, as I mentioned, determines ordering. So if you have 4 threads generating command lists, the order in which they're submitted to the command queue determines the control flow by the GPU's command processor. So one thing, we actually first attempted this in D311. It was called the deferred context. And it didn't achieve the level of performance that we wanted in the design. So we went back, analyzed the performance, analyzed where there was overhead. And there were a number of places where there was more serial overhead than we wanted in the design. So we were getting poor scaling across cores. Some of them we've already solved actually with the CPU efficiency design. So hazard tracking. If you have 2 threads generating a sequence of rendering commands, and one was meant to happen before the other, if there were hazards, say like the first command list, you're using something as a render target, second command list, something was used as a texture. At submit time, the driver would have to look at all the resource usage, figure out, oh, the user switched from the first command list using something as a render target and the second user as a texture. I better edit this list of commands and insert the hazard resolves to make the data coherent again. So it's that late submit time knowledge that causes serialization and overhead for command parallelism on 11. Next, so D311, you could have any number of deferred contexts active at once, but that caused some overhead. So that drivers actually track state per resource. And whenever you started recording commands in a deferred context, the driver would then, for every single resource you use, allocate a little piece of memory for tracking that resource state. Keep that around while you're generating commands on the deferred context. And then when you close the deferred context, the driver would then go delete all those little small per resource state tracking objects. As you can imagine, that caused a lot of overhead and was also a problem. So in 12, at the API level, when you create the device, you just declare up front, you want 8 command lists to be generated in parallel or 12 command lists to be generated in parallel. Then the drivers in the runtime can allocate all those tracking structures up front in a single coherent chunk of memory. And thus, we've avoided all the overhead of fine-grained allocates and destroys per resource. Next, resource renaming. Similar to the hazard problem, in the 11 design, it's quite frequent to use dynamic constant buffers, dynamic vertex buffers, dynamic index buffers. Behind the scenes, there isn't one object for a dynamic buffer. There are actually multiple instances of GPU memory tracking every single buffer that was discarded. So if you have two command lists being recorded in parallel on 11, and you're calling map discard, the driver is actually forced to, at submit time, figure out, okay, they called discard 3 times. I need to go patch into this second command list, the correct discarded version of that buffer. So once again, we have submit time patching of commands that's inefficient. Ideally, when the commands are generated on the parallel thread, the driver knows exactly which region of memory to use. The way we've done that in 12 is we've given your application control over renaming. There's no more dynamic buffer. Instead, your application has fine-grained fences, as I mentioned earlier. You can build your own heap allocator, your own linear allocator, subdivide a large buffer into however many renamed instances you want, and then the commands can refer to the exact point in memory in the buffer you want. So, and last, resource lifetimes. So in 11, as I mentioned before, with CPU efficiency, the runtime and driver are tracking resource lifetime. There's a lot of reference counting. That all has to get resolved and combined at command submit time, which is, again, serial overhead. For CPU efficiency, we've already given your application control over lifetime, so that overhead goes away as well. Tackling those 4 items actually makes parallel command generation extremely efficient in D3.12. I'll show you in a bit with a demo. Some implementation details. So we made some concessions in the bundle design for tiled renderers. There are also some concessions here to make sure that tiled renderers remain efficient. You don't want there to be fence operations on a fine-grained basis inside a command list. We want to let tiled renderers actually bundle a whole scene together across multiple command lists and then only fence when the entire scene is done. So fence signals and fence weights don't happen at command lists or in bundles. Those happen on the command queue themselves. So you can do command queue granularity fencing operations. Typically, as I mentioned at the beginning, the correct way to do fencing and renaming, lifetime management explicit in the app is approximately once per frame. So you don't really need fine-grained fences. You just need one at the end of a long sequence of command lists. Last, an area I'm not going to go into details on, but at the same time as D3.12, we're building a new driver model. We're building WDDM2.0. And WDDM2.0 has some kernel optimizations to further optimize the cost in submitting a command list, trying to squeeze down that serial submission cost to as small as possible, thus enabling maximum parallelism across the CPU cores. So let's take the bundle example and now make it multi-threaded. What you see on screen on the far left, that's a command queue. That represents the sequence of submissions to the GPU. In the middle, you see 2 command lists. And we're going to have CPU threads generating commands in parallel, both on command list 1 and command list 2. Then finally, for completeness, just to show the whole GPU control flow, there are 2 bundles that have already been baked before the scenario began. So let's start here. Let's say an application is starting its frame. It looks at its scene graph and decides, okay, I've got a sequence of commands to generate. Let me spawn a thread and create a command list for that rendering. And that's going to happen on thread 1 and command list 1, which you see on screen. Next, that same master control thread has decided, okay, I've got another part of the scene graph that can be generated in parallel. Let me spawn another task to generate those commands. So now we have 2 CPU threads generating GPU commands in parallel simultaneously. That first thread is finished. So what happened is it closed that command list. Those commands got baked into GPU hardware commands. That thread number 1, will submit command list 1 to the command queue so the GPU can start executing. You'll see that the GPU control flow start at this point. Meanwhile, in parallel, the CPU on a different thread, on thread 2, is still generating the commands for command list 2. So let's see that. CPU on thread 1 submits command list 1 to the command queue. The GPU wakes up and pulls it off to start executing commands. Now the CPU is generating command list 2. while the GPU is executing commands on command list 1. And you can see the bundle and the control flow there as well. Now thread 2 has finished command list 2 and wants to submit that to the queue. We'll see thread 2 submit it to the command queue, but the GPU isn't going to start executing immediately because the queue represents the serial order of commands in the GPU. So CPU on thread 2 inserts that command to the command queue, but the GPU will continue executing on its current control flow. Both CPU threads are quiet. The CPU is just waiting for the GPU to complete its work. The GPU has finished processing command list 1, and now it goes back and looks, command list 1 is done. Is there any other work in the command queue? There is. It'll pull off command list 2 and start executing. And then finally, at the end of the frame, it sends a signal telling the app, whatever resources that are transient, that were just in use for that frame are now free, and your application can reuse that memory however it wants. And that represents parallel command generation with bundle reuse, multiple threads, efficiently generated commands. Okay, so I mentioned resource renaming, how your application is responsible now for resource renaming to make command generation parallel. We want to make that easier for your app. So if you look at the 11 design, 11 has strongly typed buffers. When you create a buffer, it's either an index buffer, it's a constant buffer, or it's a vertex buffer. And in reality, one of the common requests we heard from developers, you want to be able to recast and reuse that memory however you want. And that will also enable some greater efficiency when doing renaming yourself in your app. What we've done in 12 is we've done exactly that. Buffers for streaming from the CPU to the GPU are no longer typed. So it's just a chunk of memory. You can allocate a 2 meg buffer, an 8 meg buffer, however much you need to represent an entire frame or multiple frames of rendering. And then you can implement a linear allocator, again, a heap allocator, and subdivide that into indices, constants, vertices, however you choose. We've come up with a standard alignment. So across all those types, as long as you align your data to that standard alignment, all GPUs can read in data. And finally, those buffers, it's no longer necessary to call map on map. That buffer is persistently mapped. That address is known by the CPU at all times. So you could even get parallelism on multiple CPU cores by telling a thread, I've got this region of memory, go figure out what constants I need for particular rendering. That can be completely parallelized, written, and then finally your task management system can pick that up and issue rendering commands using that parallel generated memory. Again, just from a visual point of view, the top is strongly typed 11 style. Individual buffers have strong types. At the bottom, D3D12 approach, it's just a heap, a chunk of memory. Your application can choose how to use that memory however it wants. So summarizing CPU parallelism, D3D12 has vastly increased the different parallel domains available to your application. You can do parallel command list generation. You can do parallel bundle generation, parallel PSO creation. We've extended the existing 11 model for doing parallel resource creation as well. And finally, with persistently mapped buffers, you can do parallel dynamic data generation on multiple CPU threads simultaneously without synchronizing with your rendering thread. So in summary, the runtime and driver are now designed for complete parallelism, enabling you, the developer, to parallelize your engine however you choose. The API is no longer constraining how you design and forcing you down a single path. You can design your engine to parallelize however makes sense for your content. Okay, so I mentioned we have a little more general engine than just sample code, and it's 3D Mark. So this is a machine running a shipped 11 driver, available to anyone. You can download it. And my team, working with FutureMark, took 3D Mark and instrumented it a little bit. So what you see on the top is just a visualization of the rendering workload across multiple cores. On 11, the main application thread, represented on thread 0, is vastly greater overhead than the secondary threads on 1 through 3. This is obviously not ideal. The latency and the time, the wall clock time necessary for generating a frame is solely determined by that top thread, and work isn't efficiently getting parallelized across all the cores. It gets even worse if we subtract out the application workload. So the application is getting parallelized, but this is it looking just at the graphics stack. So all the CPU overhead, starting from entering the D3D API, executing through the graphics stack, user mode driver, kernel mode driver. That's what it looks like. There's almost no work occurring on the secondary threads. All the graphics workload, all the command generation is happening on thread 0. Let me turn that off for a second. Just as a note, you'll see on the top there are, the main CPU overhead is indicated with zeros. The pluses indicate serial operations inherent in the design of 3D Mark. We just want to make sure you could see that we didn't go and do unfair optimizations to 3D Mark. Any optimization that could have been done to the 11 path, in addition to the 12 path, was left alone. When I show you the 12 version, you'll see that same serial overhead still exists. That's just how they designed the app. Okay. This is D3D12. As you can see, we have almost perfect scaling across the cores, except for the serial workload the application was designed to run. First of all, it's quite a bit faster than 11. Those are the CPU efficiency gains that we designed into 12. And then the scaling across cores, you can also see. If I switch it to show the graphics overhead, it's evenly split across the cores. You might also notice that we've gone from 2.5 or even 3 milliseconds per frame on each of the cores down to 0.7 milliseconds per frame. Vastly improved overhead, vastly better scaling across the cores. Now there's one more detail. I wanted to show you what bundles can really do in a real engine. And this is with bundles turned on. So let me turn them off. We've just gone from 0.6, 0.7 milliseconds per frame to 1.3, 1.4 milliseconds per frame across all the cores. So we were effectively doubling our CPU efficiency with bundle usage. When we ported 3D Mark, actually, we were trying to figure out how to retrofit bundles efficiently into the engine. And what we did, actually, is we ripped out a bunch of redundant state set logic in 3D Mark and replaced it with a bundle cache. So we aren't actually recording multiple draws in each bundle. It's just a single draw. What's getting bundled together are the shader state, the table changes and the constant buffer changes, along with a single draw referring to them. So we got 2x performance improvement just bundling state change with draw. Okay. So, numbers. This, if we capture a typical frame in 3D Mark, this is how it breaks down in overhead. You can see main thread, significantly longer duration of time. The overhead is split between app logic, the D3 runtime, user mode driver, Windows kernel, graphics kernel, the kernel mode driver, and present. On the secondary threads, there really isn't much graphics work going on at all. There's just the D3 runtime recording rendering commands. The user mode driver isn't even involved generating hardware commands because of the 11 design. Now if we move to 12, vastly decreased overhead on the main thread. The kernel optimizations from WDM 2.0 are taking place, so you don't see much kernel overhead at all. And you see the user mode driver involved in all the threads, the main application thread and the secondary threads. And that's showing true command generation parallelism in the D312 design. You might have noticed also that the app logic decreased in time. And again, I mentioned we actually went out of our way to make sure we weren't doing unfair optimizations. The app logic decreased in time because of how we implemented bundles. When we ripped out all that redundant state change logic and replaced it with a bundle cache, that was more efficient in the app logic than the original fine-grained redundant state tracking. Side-by-side in numbers. So overall latency, wall clock time, you can see that thread 0 went in the graphics-only stack from 5.7 milliseconds to 1.17, 5x improvement. The secondary threads, the graphics stack overhead actually went up, but that's because we're generating commands in parallel. So we have parallel generation of commands across multiple cores, and we have a relatively even workload between thread 0 and thread 1 through 3. If we sum that all up to look at the overall CPU time used, the graphics stack is approximately twice as efficient as it used to be, along with the benefits of scaling across cores. And so that's D3012 from a high level. In summary, greater CPU efficiency, generating commands, greater reuse of commands, greater CPU scalability, even scaling across cores and efficient parallelism of commands. To put a number out there, we have running workloads where we see across 4 cores, 3.5 or even higher scaling. Finally, you, the developer, have greater control over what your application can do. You're in control of how to parallelize your workloads. You're in control of the memory. You determine how the graphics stack should behave, not the driver, not the OS. Just thanks. These are all the people who have been involved in getting D312 to its current state. And we're looking forward to working with you, the developers, to make it an even better API before we ship. Just to follow up, you can look online. There's a DirectX blog. There's a sign up later this year. We'll have an early access program where you can get access to D312 before it ships. And meanwhile, look at the DirectX 12 Twitter. As we do more conferences and release more API details, you'll see notices there. And please participate in the process. I'm open for questions if anyone has them. Please use the mics.
Just curious, in previous implementations using, say, DirectX 10 or before, there was an emphasis on sorting all your draw calls based on state changes. Is that still important?
It still provides some benefit. So what we found with the 12 design is it's so efficient generating commands for the GPU that we can saturate the command processors on the GPU. And the ideal sequence of commands will be both low CPU overhead and not overburden the command processor. State sorting has less of a benefit, but some driver implementations for 12 we still expect will reduce the number of command processor commands based on coherent pipeline states being set.
Thanks.
So the persistent mapping that you mentioned for the memory,
Yep.
Is that a utility function of the DirectX runtime? Will it manage will you have a sub-allocator utility capabilities inside the SDK? And also, does it replace DD lock?
Okay, so I'll repeat the question. In general, what I heard was you're curious how the persistent mapping works, whether it's runtime behavior or SDK behavior, and then does it replace the overall map-unmap or lock-unlock pattern?
Correct.
So in general, it's behavior of the runtime. Just when you allocate one of these new buffers that are untyped, you can get the base pointer at that time and reuse that base pointer anytime in your application. So it's a behavior of the runtime itself. Your application can build a sub-allocator, a linear allocator, heap allocator on top of that. You could use something open source available for doing allocation if you want. The runtime just gives you the pointer and the size. And you can do whatever you want. As far as, sorry, your second question was just about map-on-map. Map-on-map still exists in the API, but not for these untyped buffer types. So the replacement for dynamic buffers, that's persistently mapped. We will still have map on map for things like textures and video memory, but we're going to make it more flexible so you'll be able to access GPU memory directly instead of having to copy to staging and patterns like that. So it still exists, just it's on a type-by-type basis.
Hi, this looks pretty amazing, but has it been decided yet if it's going to be backported to Windows 7?
Yeah, we actually aren't announcing any of our shipping plans yet, so I would just stay tuned to the blog and watch when we can announce our ship plans for this.
All right, sounds good, thanks.
On the blog, you told that it should be compatible with every DirectX 11 feature level GPUs. Are there any chance to make this portable to lower feature levels too?
So the feature level range for D3D12 is actually from feature level 9.3 all the way up to 11.2 and beyond. It's going to be available for a large number of GPUs out there today. If you look at, we did this series of talks 2 weeks ago in GDC. A number of the slides and the presentations there go into the exact market share we expect to have in 12. I believe the answer is something like 50 to 80% of GPUs shipped today will be D3D12 capable, and 80+% of GPUs in the 2015 timeframe will be D3D12 capable. Pretty much if you buy a modern piece of hardware today, it can run 12.
And is it the same for tablets and SOCs and
Sorry, is it?
on system on the chips and on things like that? It will be the same amount? For example, if I have a Snapdragon 800, will it run DirectX 12?
Yeah, so D3D12 is being shipped on phone, tablet, PC, and Xbox One. It covers the entire spectrum of Microsoft platforms. And the API will be consistent across them all.
Hi. We heard about a thing called WDDM2 back in about 2006 at WinHec,
Yep.
where the priorities were fine-grained context switching, unified virtual memory in 2.0 and 2.1, as the roadmap then was. Are they still on the roadmap? Because you're talking about a new WDDM2.
Yes.
Does that have those ancient Vista Longhorn era features, or are they gone?
I can give you the decoder ring. So yeah, you shouldn't assume that the 2.0 talked about then is the same as the 2.0 now.
Yeah.
But this current 2.0 has a lot of what we talked about back then. It's just taken the hardware a while to catch up with the vision.
Yeah, because AMD are kind of doing it, and NVIDIA say the next generation but one will have some of these.
Yeah, different GPU vendors are catching up at different times. So when I talk about WDDM 2.0 today for however we ship D3D12, really we're going to have multiple pieces of functionality. We'll have fine-grained memory management, page-based with GPU virtual addresses. And then we'll have some degree of preemption. The main bottleneck in preemption has always been the 3D pipeline. It's very hard to context swap 3D. There's a lot of fixed function state. The state vector is actually rather large. So it's a in some cases a 2 megabyte state vector. So you can imagine trying to context swap that multiple times per frame turns into significant bandwidth on the GPU and memory. But having fine-grained context swapping for compute tasks is certainly in order for WDDM 2.0.
Another question, if I can. So at GDC, NVIDIA and AMD actually said, with OpenGL extensions available today, we can do everything that Mantle and DirectX 12 will do, and more, with the sparse bindless texture arrays and multi-draw indirect and all these other extensions, and that they will go beyond what Direct3D 12's performance is. Do you have any answers to that? Is that true? Is that accurate?
So I don't know if they said it goes beyond D3D12 since
Well,
they didn't know what it was.
I think they said that Mantle and Direct3D 12 were very focused about building the command lists, and that was kind of it.
So D3D12 will be extremely high performance. And the other important detail is it's giving your application control over how to generate your workloads. when you start talking about taking an API with an 11 style model, you have to call it in a certain sequence to get the performance enhancement. So I believe 12 has all the same and more efficiency ideas, but in addition, it has a very flexible architecture, so you can structure your engine how you want it to be, not how the API dictates it should be. Yeah. I'll take more questions down on the floor. Thank you.